In mathematics, groups and coding theory is a very important topic. So today we start with the some topics from groups and coding theory. Now the first unit is integers, result. Now the next point is equivalence relation. Now first see what is the meaning of relation. See, let A and B be non-empty sets. Then a relation R from A to B is a subset of A cross B. That is the Cartesian product of A cross B. Now what is Cartesian product of A cross B? Now it is nothing but set of all ordered pairs A comma B where A is from A and B is from B. So if you consider any subset of A cross B, then it defines a relation from A to B. Now members of A cross B are in the form of ordered pair. Now the word ordered is very important because while forming that pair, first element we are taking from first set A and second element from second set B. That's why that pair is called as ordered pair. Now see the remarks. If ordered pair A comma B is present in R, then we say that A is related to B by R and we write this as A R B. That means A is related to B. Now if A and B are equal, A equal to B, then we say that R is a relation on A instead of saying R is a relation from A to A. Now see this example. Suppose A is equal to 369 and B is equal to 4812. Now what is A cross B? So here we have to form all the pairs by taking first element from A and second element from B. So first of all we fix first element of that pair as 3. Now we are varying the second element from B. So form the pair as 3, 4, 3, 8, 3, 12. Now as all the elements of B are finished, change the element of A as 6. Now 6, 4, 6, 8, 6, 12. Now change the element of A as 9, then 9, 4, 9, 8 and 9, 12. So as A contains 3 elements, B contains 3 elements, A cross B will contain 3 into 3, that is 9 such ordered pairs. Now if I consider any non-empty subset of A cross B, then it defines a relation from A to B. Now see some relations from A to B in this case. Say R1 is equal to 3, 4, 3, 8 and 6, 12. So all these three pairs are taken from A cross B. It means R1 is a subset of A cross B. Similarly, R2 is 3, 12, then 6, 4 and 9, 8. So again, all the pairs present in R2 are members of A cross B. So R2 is a subset of A cross B. Now R3 contains only one pair which is 9, 12. So again R3 is subset of A cross B. So here R1, R2, R3 all are subsets of A cross B. So R1, R2, R3 are relations from A to B. In this way we can define many relations from A to B for the given sets A and B. Now, see some types of relations. Now, first is reflexive relation. A relation R on a set A is said to be reflexive if A comma A belongs to R for all A belonging to A. That is, A related to A for all A belonging to A. So, what is the meaning of reflexive relation? If we are considering any set A and R is some relation defined on A, then every element of A must be related to itself. Then only that relation is reflexive relation. Now, second is symmetric relation. A relation R on a set A is said to be symmetric if for any two elements A comma B in A related to B implies B related to A. That means if A is related to B, then in that case B is also related to A. See the symmetric relation. So whenever A comma B, that ordered pair is present in R, then at that time B comma A must be present in R. And if this is true for all AB in A, then we say that the relation is symmetric relation. Now the third relation is transitive relation. A relation R on a set A is said to be transitive if A R B and B R C implies A R C. That means if A is related to B and B is related to C, then in that case A must be related to C. In other words, if we are writing relation in terms of ordered pairs, then whenever A comma B is present in R and B comma C is present in R, then in that case ordered pair A comma C must be present in R. So in that case we say that the relation is transitive relation. Now see what is the meaning of equivalence relation. A relation R on a set A is called as equivalence relation if it is reflexive, symmetric and transitive. So if the relation R is satisfying all the three properties, then that relation is considered as equivalence relation. Now to clear all these definitions, see one example. Consider the relation on set A equal to 1, 2, 3 defined by R equal to this relation. Show that R is an equivalence relation. Now to show that R is an equivalence relation, we have to show that R is reflexive, symmetric and transitive by definition. Now recall the definition of reflexive relation. Now relation R on A is reflexive if A belongs to R for all A belonging to A. If the relation is defined in terms of ordered pairs. Now here the members of A are 1, 2, 3. So if 1 is related to 1, 2 is related to 2 and 3 is related to 3, then the relation will be reflexive. So just check the pairs 1, 1, 2, 2, 3, 3. Are they present in R or not? Now see 1, 1 is present in R, 2, 2 is present in R and 3, 3 is present in R. So we are not interested in the remaining pairs for reflexivity. Just check 1, 1, 2, 2, 3, 3. So all these pairs are present in R and hence the relation is reflexive. But see, if only 1, 1 and 2, 2 are present in R and 3, 3 is not present in R, then that relation cannot be reflexive relation. So for every element A in A comma A must be present in R. Then only the relation is reflexive. Now second is symmetric. Now for symmetric relation, for the pair AB in R, check for the pair BA. So for every pair AB, if BA is also present in R, then the relation is symmetric. So just check every pair and its reverse pair is present in R or not. Now for 1, 1, 2, 2, 3, 3, obviously the reverse pair is itself. So not necessary to check these pairs. Now for 1, 2, 2, 1 must be present in R. So check that. So for 1, 2, 2, 1 is here. Similarly for 3, 2 the reverse pair 2, 3 is there. It means 3 is related to 2. Then 2 is also related to 3. Again for 2, 3 the reverse pair is 3, 2. For 3, 1 it is 1, 3 and for 1, 3, 3 is 3, 1. And for 2, 1, 1, 2 is already there. So for every A comma B in R, B comma A is also present in R and hence the relation is symmetric. So for 2, 3 pairs you can check and then for remaining pairs just check orally that for AB in R, BA is also in R. Then you can say that the relation is symmetric. But for at least one pair AB, if you are not getting BA in R, then the relation is not symmetric. Now the third is transitivity. Now for transitivity, start with the first pair as 1, 1. Now here, if you compare it with AB, A is 1 and B is 1. So the next pair you have to consider is of the type B, C. It means the first element of that ordered pair must be 1. So for 1, 1, 1, 2, A, C will be 1, 2. So 1, 2 is already there. So in this way, you have to consider pairs of the type AB, BC, and then for that you have to check whether AC is present in R or not. See, for 1, 2, 2, 1 in R, because these pairs are of the type AB, BC. So just check for A comma C. A comma C is 1 1 and 1 1 is present in R. Similarly for 3 2 2 3 in R, A comma C is 3 3, it is in R. Similarly for 2 3 3 2 in R, 2 2 is present in R. In the same way for all A comma B in R and B comma C in R, A comma C is also present in R for all A B C in A. Hence R is transitive. So here we have shown that the given relation R is reflexive, symmetric and transitive, and hence the given relation is an equivalence relation. Now one more example. Let R be the relation on the set of real numbers R such that A R B if and only if A minus B is an integer. Show that R is an equivalence relation. Now again we have to show that R is reflexive, symmetric and transitive. But the difference is that in previous case the relation is defined on finite sets. So relation is given in terms of ordered pairs. But here R is an infinite set and by definition A is related to B if and only if A minus B is an integer. So such pairs will be infinite in number. So it is not possible to write each and every pair in that relation. So here it is defined in this way. Now see how the elements will be related according to this relation. So the real number A is related to B if and only if A minus B is an integer. For example, if I consider A is equal to 6 and B is equal to 4. Now 6 and 4 both are real numbers and 6 minus 4 equal to 2 is an integer. So I can say that 6 is related to 4. Again if I consider A equal to 10.5 and B is equal to 8.5. Again both are real numbers. Now 8.5 minus 8.5, 10.5 minus 8.5 is 2 which is an integer. So 10.5 is related to 8.5. So in this way, the relation is defined as A related to B if and only if A minus B is an integer. So here you can take A and B as any real numbers. Now first we show that R is reflexive. Now to show that R is reflexive, we have to show that A related to A. Now by definition, A will be related to A if and only if A minus A is an integer. So just find A minus A. So whatever A is there, A minus A is always 0 and 0 is an integer. So A related to A for all A belonging to R. That means R is reflexive. Now second property is symmetric. Now in symmetry we have to show that whenever A is related to B, then B is related to A. So we start with the assumption that A is related to B for two real numbers A and B. Now by using definition of relation in this case, A related to B implies A minus B is an integer. Now concentrate on the thing that we have to prove, that is B related to A. Now by definition B will be related to A if and only B minus A is an integer. Now here we got A minus B is an integer. Now we can write B minus A as minus of A minus B. But see, A minus B is an integer. So minus of A minus B is an integer. That means B minus A is an integer. So again using the definition of relation in reverse way, B related to A. Thus, A related to B implies B related to A for all AB belonging to R. Hence, R is symmetric. Now, the third is transitive relation. Suppose A, B, C, these are three real numbers such that A related to B and B related to C. Now, by using definition of relation, we get A minus B and B minus C are integers. Now, we have to show A related to C. That means A minus C is an integer. Now, see, as A minus B, B minus C are integers, their addition is again an integer. Means A minus B plus B minus C is an integer. So, A minus C is an integer. That means again by using definition of relation, A related to C. So A related to B and B related to C implies A related to C for all A, B, C in R. Hence, the relation is transitive relation. Thus, relation is reflexive, symmetric and transitive. Hence, it is an equivalence relation on R. Now, the next is congruence relation on a set of integers. If a and b are integers and n is a positive integer, then we say that a is congruent to b modulo n if n divides a minus b. See, a and b are any integer, so it may be positive, negative or 0 also. And n is a positive integer, that means n is a natural number. So whenever the natural number n is dividing a minus b, then in that case we say that a is congruent to b modulo n. And we write this as a is congruent to b modulo n. Now, whenever a is not congruent to b modulo n, that means n is not dividing a minus b, then we write this as a is not congruent to b modulo n. And we say that a is incongruent to b modulo n. Now, see this example. 16 is congruent to 11 modulo 5. Now, comparing it with the standard notation, here a is 16, then b is 11 and n is equal to 5. So 16 minus 11 is 5 and his n equal to 5 divides 16 minus 11. So 16 is congruent to 11 modulo 5. Similar way 3 is congruent to minus 5 modulo 4 because 4 divides 3 minus minus 5, that is 8. But 17 is not congruent to 3 modulo 5 because 5 does not divide 17 minus 3, that is 14. Now see next theorem. If a, b, x belong to z, that means they are integers, n in n means n is a natural number and a congruent to b mod n, then a plus x is congruent to b plus x modulo n, and secondly ax is congruent to bx modulo n. Now the proof is very simple. We have to use just definition and concept of divisibility. Now, what is given to us? A is congruent to B modulo n. So, this part is common for both the proof. So, A is congruent to B modulo n. By definition, we can say that n divides A minus B. Now, from concept of divisibility, A minus B is equal to n into k for some integer k. Now, we call this equation as 1. Now, first result is a plus x congruent to b plus x modulo n. By definition of congruence, we have to show that n divides a plus x minus b plus x. So we start with a plus x minus b plus x. As there is negative sign outside the bracket, by changing the sign of every term we get it is a plus x minus b minus x. So cancelling x, it is just a minus b. But from equation 1, a minus b is n into k, where k is an integer. So finally we get a plus x minus b plus x is equal to nk. So again by using definition of divisibility, we get n divides a plus x minus b plus x. So by definition of congruence, we can write a plus x congruent to b plus x modulo n. So this is the proof of first part. Similarly, see the second part, x congruent to bx modulo n. It means we have to show n divides ax minus bx. So we start with ax minus bx. So again taking x common, this is x into a minus b, which is x into nk. So it is n multiplied by xk. Now as x is an integer, k is an integer, x into k is an integer. So by using definition of divisibility, we write n divides ax minus bx. Implies by definition of congruence, ax is congruent to bx modulo n. Now, one more theorem. If A, B, C, D belong to Z and n is in n, A congruent to B modulo n, C congruent to D modulo n, then A plus C is congruent to B plus D modulo n. Second, A minus C congruent to B minus D modulo n. And third, AC is congruent to BD modulo N. Again, the proof are on the similar lines. We are using just definition of congruence, divisibility. Now, according to given information, here we can write n divides a minus b, and from this n divides c minus d. So, using definition of divisibility, we get a minus b is nk and c minus d is equal to nl for some integers k and l. Now to prove this first part, we have to show n divides a plus c minus b plus d. So start with a plus c minus in bracket b plus d. Again changing the sign of b and d, it is a minus b plus c minus d. So from this equation, it is nk plus nl. So finally it is n into k plus l. So by definition of divisibility, n divides a plus c minus b plus d, as k plus l is an integer. So by definition of congruence, a plus c is congruent to b plus d modulo n. Similar way, we can prove second part. The only thing is, instead of a plus c minus b plus d, we have to consider a minus c minus b minus d. Now see third part, AC is congruent to BD modulo N. So we have to show N divides AC minus BD. Now here the first step is very important. So you have to remember this step. Otherwise we can't do further. So AC minus BD is equal to AC minus BC plus BC minus BD. So here we are doing one adjustment, that we are subtracted BC and added BC. So from first two terms we can take C common, and from last two terms we can take B common. Why we are doing this part? Because we have the values of A minus B and C minus D. So using that values, it is C into NK plus B into NL. So again, by taking n common, it is n into ck plus bl, where ck plus bl is an integer. So by definition of divisibility, n divides ac minus bd. So by definition of congruence, ac is congruent to bd modulo n.